Hi everyone, this is Dr. John. Today we're going to practice solving this NMR. So the 1H NMR spectrum of a carbonyl compound with the formula C4H8O is shown below. The numbers above the peaks are relative areas. Give the structure of the compound and label the protons in the molecule with the same label as the peaks. So I see 3 peaks here. I better give them a letter A, B, and C. So I'm told that I have a carbonyl compound. That information probably came from an IR. The first thing I like to do to start, I've already done a few things, is to calculate the degrees of unsaturation or double bond equivalent from that formula. So you can do that by simply drawing any correct formula and counting the double bonds or rings, or you could take 2 times the number of carbons, which is 4, plus the number 2, plus any nitrogens in the formula, which we don't have any here, minus the number of hydrogens in the formula and halides, which we don't have any here. Oxygen doesn't come into the equation because it doesn't change the number of hydrogens in the formula. Divide it all by 2. So we have 8. So it's 2, 10 minus 8, 2 divided by 2, 1. So there's 1 double bond or 1 ring. We already know this is a carbonyl compound, so that accounts for all of the double bond equivalents. So that's step 1. Step 2 is to check the integrations. So we should have 8 hydrogens because that's what the formula says in the molecule. So the integrations must add up to 8. So my integrations right now are 1 plus 1.5 plus 1.5, but that only adds up to 4. Right? So I have to correct the integrations. Right? So to correct the integrations, take the number of hydrogens in the formula, right? 8 hydrogens in the formula divided by the sum of the integrations, which is 4, then you get a 2. So then I need to multiply all of my integrations by 2. By 2. So HA is not 1 hydrogen, there are actually 2 hydrogens under that same environment. HB is 3 hydrogens, so 3 HBs. And HC, it's actually 3 HCs. So my integrations are corrected. Then the next step I want to follow is to go 1 peak at a time. And I'm going to start with HA here, the most de-shielded. Determine the multiplicity by simply counting the lines 1, 2, 3, 4. See how the relative intensity is there? It's like 1 to 3 to 3 to 1. That is a quartet. So the multiplicity for that peak is that of a quartet. So a quartet is that n plus 1 to 4. That means that CH2 or those 2 hydrogens have 3 neighbors or n. Right? Simply just solve for n there. So every time I analyze a peak, I'm going to try to propose a piece of the molecule. The integration is of 2, so that suggests a CH2. Okay, I mean, it could be 2 CHs, okay, but CH2 is a good place to start. And those 2 CH2s need to be split by 3 neighbors. So I'm going to guess a CH2 next to a CH3. It could technically be a CH2 next to a CH and another CH2, but the NMR has to be redundant. Okay, there are not that many peaks here, there are only 3 peaks. So proposing 2 other different environments around that CH2, it's not really a good way to go. Propose simple structures and then try to corroborate them with other peaks. And if you can't, then propose more complex structures. Okay. So now I'm going to move on to peak B. So HB, there are 3 of them. So that's probably a CH3 or likely could be a CH3. The multiplicity is that of a singlet. It's 1 line. So then 0 neighbors. Okay. So then I'm again going to propose a CH3, but it's not next to any other hydrogen. So what does that mean, being next to any other hydrogen? Well, if I draw out this ethyl that I do a little bit more, right there, my H not HAs, not HBs, and draw the CH3 a little bit more. Okay, these are neighbors, right? These are neighbors. They are 1, 2, 3 bonds away. That's a neighbor. So B here doesn't have any neighbors, so we don't expect to have any carbons with hydrogens 3 bonds away, or maybe even 4 bonds away. Although 4 bonds away, sorry, 4 bonds away, it's starting to get pretty far. So you can consider neighbors really just 3 bonds away. Okay, so it's good to point out that these are not the same CH3s, right? These are not the same CH3s. So then my last peak better be for that CH3, or else I don't actually have what I proposed up here. So this last peak, the integration of 3, so I think that's a CH3, the multiplicity 1, 2, 3, that's a triplet. You have that relative intensities 1 to 2 to 1. And by that I mean the intensities of each line in the multiplet. Okay, 1 to 2 to 1, that's a triplet. So the number of neighbors is 2. So that's consistent with what I have here. A CH3 labeled C there being split into a multiplet by a CH2. Okay, so I can try and put all the pieces together. I know I have a carbonyl. I know that I have a methyl that doesn't have any neighbors, and I think I have an ethyl. So the best thing to propose here really is a ketone, right? A ketone. Okay. So now that I proposed the molecule, I'm going to look at the chemical shifts and make sure that they make sense. Okay, so I'm going to go to my next table, to my tables. I'm going to go to the next slide here. Draw the same molecule, CH3, CH2. I'm just drawing the correct. Okay, I'll make a little more room. My table is way too big. CH3. Okay. And then I think my labels were A, C, and B. So the chemical shift for hydrogens that are 1, 2, 3 bonds away from the oxygen of a carbonyl, the electronegative atom, should be similar to that for a methyl ketone. And this is a methyl ketone, 2 to 2.4. Similarly for CH2, the CH2 here, it should be 2 to 2.4 because they are also 1, 2, 3 bonds away from that carbonyl oxygen. Now there is a CH2 here on the table, right? There's a CH2 here on the table, but I'm not going to use that range because this is really for a CH2 that is not deshielded by any electronegative atoms. So that of an alkane or a CH2 that's more than 3 bonds away from an electronegative atom. So both of these hydrogens should be about the same chemical shift. And then this CH3, which is pretty far away from the carbonyl oxygen, should be close to 0.7 and 1.3. So it's more like the methyl at the end of an alkane. Okay, so then let's go back to our NMR. So here's 2, okay, and 3. So both of these peaks are between, let's say 2 and 2.4. So here's 2.5. And we really measure the center of the multiplet. So those are right within range. And this peak here is right within range, 0.7 to 1.3. So then our structure makes sense in terms of the chemical shifts. It's good to double check the multiplicities in the integration. So I should have a peak with an integration of 3 split into a triplet. I have that. With a chemical shift that's pretty outfield, I have that. A peak with an integration of 2. I have that, and it's split into a quartet by 3 neighbors, right? That's this peak here. And the chemical shift should be that of a methyl ketone, according to my table, even though that's not a methyl, it's a methylene. And then I do have a methyl here, integration of 3, no neighboring protons. So no protons that are 3 bonds away from those 3 hydrogens. So a singlet, and then the chemical shift, that for a methyl ketone. So everything's consistent. This molecule makes sense. All right, if you found this helpful, please give it a like and subscribe for more videos. Thank you.